It is my pleasure to introduce today's speakers, and we actually have 5 speakers. 2 are present here in the room, and the 3 others join online or will join online later when they are free. And I would like to start with Gustav Smidt, who has an MA in Assyriology from the University of Copenhagen and also formal training and programming from the same university. And his interest within Assyriology lies in the Old Babylonian period, which has an abundant variety of texts. He has employed simple scripts, and scripts in the sense of code, for the studies to deepen his research, and has since then worked on geomapping landscapes of writing projects at the University of Uppsala, where digital and computational methods were employed to assist in data gathering and analysis. He is currently working at the Cuneiform project that will be presented today as a PhD student at the University of Gent, trying to connect the dots between Assyriologists and specialists in digital and computational humanities. And to him, that means respecting the fair data principles, and to ensure that the cooperation between Assyriology and digital humanities is a fruitful one and a positive influence for ancient studies. And the second speaker who is with us here in the room today is Lefever. She is an associate professor of computational semantics at the Language and Translation Technology team at the University of Gent. And that is a team that conducts fundamental and applied research on different levels of natural language processing from a corpus-based perspective. And the team has extensive expertise in the use of machine learning for a wide range of language technology problems. And Els heads the research lines of computational semantics and terminology in that team, and she has a strong expertise in machine learning of natural language and also multilingual natural language processing, with a special interest for semantics, so computational semantics, cross-lingual word sense disambiguation, and multilingual terminology extraction. And she supervises also several PhD theses on language modeling of low-resourced languages, including languages written in cuneiform or Byzantine Greek. And then the third one, who will join online later, is Lefever. She is also an associate professor, but of Assyriology at the University of Gent, and she is the supervisor, or I guess that's the same like principal investigator of this Cuneiform project at Ghent University. And her research focuses on the socio-economic history of the Old Babylonian period, including gender history, prosopography, sealing practice, and digital humanities, and the relations between Mesopotamia and the empire of Elam in the 3rd and 2nd millennia BCE. And that includes, of course, studies on bilingualism and on border issues. And she is a specialist of Old Babylonian Akkadian. And Katrin is not here with us today because, ironically, she is currently taking part in a machine learning class, so still related to our topic, obviously. And the 4th project member is Lisa Foket. She is a PhD candidate in digital humanities at Ghent University, and she has earned her MA in history and in digital humanities from Ghent and the KU Leuven. And throughout her PhD, she is involved in multiple research projects, none of which I can pronounce properly, so I jumped that line. And her research is focused on digital cultural heritage and how to optimize it for reuse for multiple stakeholders and audiences. And for the Cuneiform project, she is involved with the creation of both a digital scholarly edition modeled towards Assyriologists, as well as the creation of a virtual exhibition. And in both, she wants to make use of IIIF, and critically analyze its benefits, as well as build up on the annotation possibilities that it offers, and towards the optimization of the usability. And last but not least, There's Krishna Chandrasekar. He is a postdoctoral researcher at the Gent Center for Digital Humanities and a scientific expert at the Royal Museum of Arts and History in Brussels. He did his PhD in computer science and is an expert in building computer vision pipelines and OCR workflows to address unique problems pertaining to the enrichment and utilization of heritage collections. His research interests include computer vision, applied machine learning, and image processing focused within the digital heritage space. So, and with this power of expertise, they now tackle this Cuneiform project using IIIF and will present that project to us under the title Mind the Gap. So thank you for coming and please enlighten us.
Thank you. First of all, I want to ask, can you hear us online or can you hear me right now online?
Yes.
Yes, and then maybe I'll put on the video here so you can actually see me speak as well. So, can you see me now?
Yes.
Good. Super. Thank you so much for the invitation, Elite. We are very happy and also to be able to be here today in the rainy and fantastic weather of Berlin. Yeah, I'll get right to it. And hopefully during this presentation, it'll be a bit clearer why Elise went through 5 names and not just the 2 of us, because it is a very collaborative effort. There we go. So quickly, the outline for this talk today will be that I'll first go over the Cuneiform project just a bit in general. Then I'll go through the hurdles that we have experienced so far and we expect to mean quite a lot for the project itself. Then there will be the IIIF, the International Image Interoperability Framework. And then Els will take over and give you a very, very basic introduction to machine learning so that you can understand what I'll be talking about in the first OCR, the optical character recognition part, and then the NLP, natural language processing. At the end, I'll quickly summarize the whole thing in one slide and just tell you what we're going to do next so that hopefully becomes clear. So the project is a collaboration between these 3 partners. We have the KU Leuven, we have the Royal Museums of Art and History in Brussels, and we have the Gent University. At Gent University, we have the Assyriologists at what we call Assyro Gent. We have Els who are in the LT3, and we have Gent Center for Digital Humanities. Our mission statement, or sort of the rules we would like to live by in our project, is very much centered around openness. We want to make sure that the stuff in the collections, either in the deep basements or in the open collections, can reach a general public and also researchers, not only researchers outside of our project, but also the researchers within the project. We want to encourage collaboration, and this especially collaboration across disciplines, because it's very difficult for us who might dabble in digital humanities or computational humanities to understand what's actually happening in those spheres. That's where we need other specialists to be able to apply state-of-the-art methodology element. This means that we have 2 groups. Mainly, we have the cuneiform specialists who will we will try to create the highest quality data possible. Which of course is very important because the models are only as good as the data input. Then we would like to try to monitor the data processing in real time so that when we go step by step, hopefully we can spot the things that are mistaken or where there's been a conversion error or something like that. And then at the end, of course, we would analyze results to try and show what is the benefits of the results we get from these methodologies. Then there's the digital and computational specialists, and just so you're clear, I differentiate between those 2. Where the digital, for in this case, is more the one working with the end user, and the computational is sort of the back end stuff, the thing where you work with a computer to grind through a bunch of stuff. But both of them is there to help ensure a very rigid data scheme so that we can make sure that the data we have and the data that we might implement from someone else is compatible with each other. Of course, it's also identify and implement and state-of-the-art analysis, as mentioned before. We want the best of the best, and as else we'll come back to, you have all probably now heard about ChatGPT, but if we go 1 year back, that will be something few people had heard about probably. So you can imagine that this area of AI and special language models evolved very quickly. And then, of course, we have the data sharing, which is essential to be open, not only inside the project, but also with people outside of the project. We are specifically interested in the Old Babylonian period. This is the area around the southern part of modern-day Iraq. And we are specifically then working with the time period from around 2000 to 1600 BCE. We are working with Akkadian only. So that means the Old Babylonian dialect of Akkadian. And I won't go too deep into what we mean by archival text. That's not too important in our context right now. But when I say archival text here, just think of like letters, documents, accounts, those sort of stuff you would expect to archive for like in private or institutional economical importance. We have three main corpora. We have tablets from the Royal Museums of Art and History, just the MRAH abbreviation. Here we have around 70 Old Babylonian Akkadian archival texts. They have been 2D plus imaged, and I'll come back to what 2D plus means. These will be conventionally published, so in journals, but they will also be digitally published. This is the part of the IIIF part to share them widely. They will also serve as well-studied cases for methodologies, so to be kind of like a baseline test for all the computational stuff we do. Then we have the OCR corpus. Here we have around 200 Old Babylonian archival texts. These are also 2D plus imaged. Here we will individually annotate and extract signs from each tablet, and we'll use that as training data for the OCR part. And then lastly, we have the NLP corpus. We have around, we want to get to every Old Babylonian Akkadian letter in theory. That's going to be difficult, but that's the goal. And here we're going to work with machine readable texts, so no images. And here we would like to have rich textual annotations of the texts, and they will serve as training data for a language model. Just quickly, we have three different legs of the chair for this project. We have the IIIF, the OCR, and the NLP. The IIIF, I will go in detail with each of them, but just quickly, the IIIF will support a widely and freely accessible API. It will provide high-quality image and functionality around these images with textual content, so translation, stuff like that. And in this way, we ensure an infrastructure that can be adjusted to a tailor-made presentation at each institution or each computer potentially. Then we have the OCR, where we want to locate signs, predict their readings, and then ultimately facilitate automatic readings, which is of course a very big goal. Then we have NLP, which is basically three steps. First, we want to automate a text annotation, enrichment of the text. We want to generate language models that we can iteratively ask questions. And then we want to quantify our linguistic analysis, which are, of course, the cornerstone of the Cuneiform and the Assyrian part of it. Hurdles. The first hurdle is around the data part, the openness of that. We experience, of course, as I think many institutions does, we expect that there's an increased sharing of data, which is, of course, positive. But we also, of course, increase competition because of the global market now. That means that there is this discrepancy between should I share something when I'm not completely ready, or should I wait for it to be completely done, and then you might never get there because you're afraid of somebody else stealing it. And it goes back to people not always being good enough to refer to stuff. So if you find a database entry online, you might not refer to it in the same way as if you have taken a lexicon down from the shelf and found a entry in there, even though in reality they might be quite similar in workload and importance. And of course, there's also the issues of people just have different systems. People don't upkeep their systems. Money runs out. You don't have any more money for upkeeping it. And this, of course, also hinders our work, but it also hinders the way we might see our own data in the future, depending on how long we expect to live on for. Then there is the linking of the data itself, because cuneiform is a very big concept. It stretches almost 4,000 years. It varies a lot across time, a lot across genre, and it's used for writing multiple different languages. This just means that even though we might have a textual format or format we see fit, it might not match anything else for let's say Elamite, a different language. This comes back to the data formats, which is a big issue we've had especially with the NLP part, and it's something we're considering and working with other people to try and fix. The cuneiform script itself, it's a 3D script. It's mainly written on clay and mainly found on clay tablets in the Old-Babylonian period. I guess for the camera, it's around this side, I guess. It's written on all sides at some times, sometimes not. But it can be written on all sides, so front, back, top, bottom, and left and right. And when writing it, it requires you to understand how do you manipulate this clay, the plasticity of the clay. So how hard do you press? How long lines do you draw when you write? Those kind of things matters. And when you don't have to read it now, 4,000 years after it was written, it requires that you understand how do you manipulate the lighting. And the example you can see here with the 3 images at the bottom, this is all the same sign on the same tablet. So the exact same sign. And the sign it should be, you can see the drawing on the right at the bottom. That's how it should look like in abstract sense. And so 3 verticals, 1 vertical followed by 2 verticals on top of each other. And if you can see on the bottom, the pictures, the one on the left, you can kind of see that there are 2 verticals. The one in the middle, you can clearly see the heads, as we call them, of the wedges of the 2 verticals. And then you actually have to go to the 3rd image to be able to see all 3 of them. So this means, of course, it makes it difficult to read, but also means it matters a lot which kind of image you have. A lot of these tablets have been scanned with flatbed scanner, which has more or less a static light application to the image. But this is very different, of course, from a 3D scan, where you can manipulate the way you look at the tablet. And then there is the last thing I want to say with the 3D reality of it, that it's a handwriting system, especially in the Old Babylonian period on clay tablets, which means that you don't have a typeset. So things are kind of on top of each other. You have sort of some sign filling one space that kind of interjects with another sign and stuff like that. Which of course makes it way more difficult to segment things and understand where does one start and where does one end. The script itself was invented for Sumerian, for writing Sumerian. There might be some Sumeriologists who disagree out there. I'm just gonna stick with that now, not open that Pandora's box. But it originated as a pictographic writing system. And you can see here the 3 images. At the top, you have 2 wavy lines that are horizontally going from one side to another. And that's the sign for water. And when this then developed, you can see I've just taken 3 steps, but of course there can be more intermediate steps in this process. But it ends up then being 3 vertical cuneiform wedges on top of each other. And this is how it looks like in the Old Babylonian period, where it is a logosyllabic script, to call it. So that means it can still hold the meaning of water, so it can still have this logographic meaning, but it can also be used as syllables. In this case, it's only an A or an A, but it goes into the syllabic system. Then we have the language of Old Babylonian Akkadian. It has very close ties to Sumerian. So I might say, almost say, inherited cuneiform from Sumerian. Akkadian uses a lot of Sumerian word signs, as we call them. Those are the logograms I talked about before. You can see here the example at the bottom. The 2 red boxes, they highlight syllabically written Akkadian words. And then the green box highlights two Sumerian word signs to mean something in Akkadian. So that can quickly become a bit confusing, of course, when it's what, and this Sumerian word signs, they don't show grammar, typically don't show grammar. There are a few examples where they can show simple grammar, but they typically don't show grammar. So that means you have to interpret what lies underneath in some sense. Akkadian is also a Semitic language, which is, well, it means it belongs to a group of languages which are quite specific in the way they behave. It's very different from Indo-European languages. They have what's called a triliteral radical structure, or at least a radical structure, and Akkadian has a triliteral, so that means there are three different consonants that sort of bear the meaning, and then you have consonant and vowels around that changes. What is interesting then is that, as I said, it's very close ties to Sumerian, and Sumerian is a linguistic isolate. That means that Sumerian has no recorded language that we can relate it to. And that helps a lot normally, that you can relate languages to each other. That means you can sort of find assumptions that you can say, okay, we don't understand this in Sumerian, but it behaves like this in a similar language or language family. So we assume it's going to be something similar. But when you then have the match of these two very different languages, it of course skews things a bit and makes it a bit complicated. Akkadian itself, in computational terms, is a low resource language. There is, like, don't get me wrong, there like a lot of text out there. So there's tons of texts for, like, if you consider it as a classicist or ancient languages in general. But as computational wise, there's very few, a very low resource. There are very few annotated resources available of Old Babylonian Akkadian specifically. From on ORAC, the open richly annotated cuneiform corpus, which is the biggest one, there's almost no Old Babylonian Akkadian texts. Even though Michael Streck, or Michael Streck, I guess, he's German. So he estimated in 2010 that around 25% of Akkadian words should be Old Babylonian. So there's a lot out of the full Akkadian corpus that should be Old Babylonian, but there is very little freely available, I should say. So the first leg of our chair here, IIIF. The objective of IIIF is, first of all, to create an infrastructure for our whole project. This infrastructure should support a digital publication, which should almost be sort of a digital twin of our physical publication, but with even more detail. So all the things we might leave out, like grammatical annotation in a physical publication, we would then include in a detailed online digital publication. This should be able to provide reusable data for everyone else, so the open access part of it. We want to also make a viewing experience to highlight what you can do with the IIIF infrastructure. So we want to share two specific views we want to show into our cuneiform corpus. We want to aim at, first of all, most researchers. That's quite a wide term, but we have the assumption that a lot of researchers just want the data, and then you can toggle on and off the things you don't need. That's kind of the assumption we're going by. And then we want to target specific public audiences. I'll get a bit more into that. We also want to make a flexible space to interact with the tablet, so you can try and move them around and do what you want with them. And from the whole IIIF framework, because if you heard about it before, you might know there's more elements to it, but we're just going to work with the image API, the manifest, and the viewers. That's kind of like the essential parts we're working with. And these are just two examples of how it can look like when you have a finished, nice product. So the image data is hosted on our service. It's accessible simply via URL, so it's quite easy in that sense. You can get it various formats, or you can get even TIFF format, which is very high quality. You can get JPEG, so you can play around with that. You have different functionality, so you have like deep zoom, you can rotate it, and you can like limit the regions. That's what I'm going to try and show you here quickly. So I have here a viewer. And as you can see here, doesn't highlight. Oh, here it does. This means that I have a box. I don't know if you can say it. It says exclamation mark 500, comma 500. That means I'm giving the URL a box of 500 times 500 pixels, wherein it can show the image. And then it fits the image within that. And does look like this. So it's a bit too big for my screen, but that's okay. And then I go in and I simply I can change it. So let's say we want it smaller. It should be within a 300 times 300 box. And want to rotate it 90 degrees. Boom. That's it. So it's those kind of things can function quite easily. And that's the whole idea about the IIIF infrastructure, that there is a basic set of function that just works easy, works well. And especially the deep zoom is like the very good thing about IIIF. Then we have the manifest data. Here we have textual data and metadata. The textual is just as much as we can provide, basically. So transliteration, translation, and grammatical information. From this, we want to pass this raw textual data so we can read it as a human, so to speak. So it looks a bit nicer for people when try to read it. That, for example, means the shin, the S with the V on top, should be how we read it instead of the S set, which might be behind it. That's because the shin with the V on top is not a basic character of all standards out there. Then we want to be able to link this data. Of course, we also want to do that with the metadata, but that's a bit more easy. But with the textual data, we want to link this as well. So you could imagine that you have a place name, personal name. You can even have like individual words. And then you have something like, well, not Wikipedia, but something called FactGrid, for example, which is like the duplicate of Wikipedia, but more open. Here you could then have a ID, which I link to with my text, and then let's say someone in Yale has the same person in their text. They link to that the same ID, and whoopsie, you have everything in there. Then we have the metadata. Here we can define structures of how we show things. This is where we can curate things and say, now you're only allowed to see these 10 images, because that's how we group things here. We also provide basic information, so you know who wrote it, where is it located, those kind of things. And what is very nice is that we're working with a data structure called triples in this instance, which means that we're having something called subject, predicate, and object. And when you set it up this way, just explain you what it is in a second, but if you set it up this way, it's very easy for, and I'll say humans again, for someone who's not the computer to understand what is happening. This is based on words. So this is, for example, the subject can be a tablet. The predicate can be is stored in, and the object is then the RMAH. So you have this sort of way you can understand as a human when you read it that it makes sense. You don't have to draw the link between tablet and RMAH. But we can still make it in a way that's, of course, compatible with other formats. So when you export it, we can match it up with like the bigger databases that exist out there who has different systems. Then there's the visualization of data. Here we have want to have a rich scholarly edition where we have tablet by tablet view. We have as much information as possible. It's dynamic and you can move things around. And you can compare different tablets, different texts, depending on what you need. And this is what we mean by it's aimed at a broad spectrum of researchers. You know, if you only want to see translations, you only see translations. If you only want to see images, you only see images. Or you're linguists and you only want to see the grammatical information. You don't have to see all of it at once. Then we have the public exhibition part. So of course you'd be engaging. Here we curate the tablets instead into specific groups. These curation will be narrative driven. So we find some sort of narrative we find interesting and want to put out there. We want to create a platform that has sort of a support for physical collection. So you could imagine that you have a small pop-up exhibition where you might not be able to have tablets. Maybe you can have 3D prints, but not real tablets. And here you then have the tablet interface, for example, like, iPad tablet interface, you can then interact with the physical Cuneiform 3D tablet. But it also means you can go home and look at the same thing online and get half of the experience if you want to. This is going to be audience-centered. This means, as I said before, we're going to focus on very specific groups. I think it's going to be some sort of lower high school, upper, it's called primary school sort of age, because we want to be able to aim a bit more specifically rather than just general public. And we also want to make sure that we get sort of heritage aspects and stuff like that. So we have, of course, a very open and inclusive way of showing this. Then Pels will take over for a minute.
Yes, I will give a very short introduction to machine learning, because for people, I'm not sure, are there people familiar with machine learning? Yes, so I can go a bit faster, then that's good. Because otherwise it will be difficult to understand the results of both the OCR and the NLP experiments that Gustav will explain. So how does a computer learn language automatically? So first, linguists or computational linguists were crafting rules or were compiling lexicons, for instance, with words and their grammatical information and so on, so we could automatically analyze text. But soon this became not feasible anymore for all kinds of NLP tasks. So that's where we turned into database approaches, and that's where machine learning popped up. So machine learning wants to give computers the ability to learn without having explicit rules or instructions made by humans. And traditionally, we make a distinction between three categories of machine learning. So we first have clustering. So there we try to group examples because they share certain characteristics. And an example of clustering is, for instance, recommendation systems, such as Amazon and Netflix and so on. You get suggestions based on characteristics they share with things you have already looked at, for instance. This is called unsupervised machine learning because you don't need labeled examples. So you just look at the characteristics and try to group examples together. And then we have two categories of machine learning that are supervised. And this means that you do need labeled examples, to build a machine learning system. So there, the first type is classification. So here you have data that is labeled with specific classes or categories, such as, for instance, part of speech tagging. So you have your data set. You have, for instance, 20 part of speech labels, and you give a label to every example in your data set. And then the third category is regression. There you don't have classes, but you try to predict a score. So an example of a regression-based approach is, for instance, automatic writing evaluation, where you want to predict a score for a given example in your dataset. So for the rest, I will only talk about classification because for the NLP experiments, we also built classifiers. Maybe something else I should mention is I will focus on NLP, so on digital text analysis, but the same principles also hold for vision recognition or image recognition. So it's the same type of images. So when we talk about classification, so we built a classifier, we traditionally have two phases. So we have a training phase where you need labeled examples in order to build a model. And then during the test phase, you can apply this model that you have built on new examples and try to predict a given class. And therefore, we need three things. So we first of all need a lot of high quality manually annotated data. We need a specific machine learning algorithm, of course, and we need features. And features are pieces of information of which you think that they can help to model the task. Yeah? So I will come back to that a bit later. So this is what the standard machine learning pipeline then looks like. We have the data preparation phase, and there the data can be images, it can be text, it can be other kinds of data. We first try to convert the data into a set of features, so important information to solve a given task. And we train a model based on these feature vectors, we call them, so these vectors containing all our information. Once we have trained a model, we can apply it on new unseen data and then predict a given label for this unseen data. So what are these features? Just to give you some intuition of how features look like. So this is a very simplified example. So assume we have a data set with 3 instances or 3 examples. They all 3 have been labeled by a human with a given class or a given label. So I have an image that is a fish, I have an image that is a panther, and I have an image that is a bird. Now, if you will think as a human, like what could be important information to distinguish between these 3 classes, what is information that a computer could use, so features, to predict a given class label. It could be the label animal, but of course, all 3 of them are animals, so that's not a distinctive feature. Maybe the color can be important. It can be black, orange, and white in case of a fish. It can be black only in case of a panther, or again, black, orange, and white in case of a bird. So this already tells us something about the class, but it's not distinctive enough. And then maybe we should add features like jaws or paws or feathers that are really distinctive features. So features are information that you can extract from your data that can learn you something about the class the example belongs to. Yeah? So then we train our model. So we train our model and then we apply it on a new example. So an unseen test example of a bird in this case. We again extract the same information. It is an animal, it is black, orange, black, and it has feathers. And then our model has learned that probably based on these features, this should be a bird. So it predicts the class label bird. Yeah, is this clear for everybody? So you try to find distinctive information that can help you to model a given task. So these features for natural language processing, so for digital text analysis, they usually are lexical features, for instance, the words that occur in the sentence or things that are in a dictionary that you can look up. It can be semantic features, but also grammatical or syntactic features. So every piece of information you think might help you to solve the task you're working on can be an important feature. Okay, so this was the more traditional feature-based machine learning, but I think 7 to 8 years ago, the neural machine learning popped up. So I think you all know ChatGPT, and you probably also noticed that, for instance, Google Translate got a lot better the last 5 to 6 years. That's also because now it is trained based on neural machine algorithms. So what is the idea underlying deep neural networks or neural machine learning? It is inspired by the way the human brain works. Yeah, so it mimics a bit how our brain works. So in our brain, we have neurons that can pass information to each other. And the deep neural networks, we try to mimic that behavior. So you also have artificial neurons where the information comes in. Then you have a number of what we call hidden layers. And the more hidden layers you have, the deeper your neural network is and the more or the better performing it will be. And then you have your output layer that also predicts a label like you would do in traditional machine. Now, how can we train such a neural model for natural language processing? The main module is a language model. So also in ChatGPT, for instance, the main part of ChatGPT is a huge language model that is trained on a gigantic corpus of text data. So when I say massive text corpus, in the case of ChatGPT, the GPT-3 model, for instance, it's 45 terabytes of data, and 1 terabyte is around 6 million pages. So it's really huge what is used to train these language models. So how does it work? It is trained with the specific task of predicting the statistically most probable next word. So that's the task that is given to the algorithm to train the language. So if I ask you, for instance, whisk together the flour, baking soda, and a pinch of, what would you answer?
Salt.
Salt in a large bowl, or I prefer a glass of
Rosé.
Rosé. Here you can already feel you have more options, and this is exactly how a language model works as well. So it tries to learn based on this huge set of textual data what the most probable next word is. And it's not only one word in most cases, but a variety of words that can fill this slot, but they have a certain probability. Yeah? So the algorithm or the architecture that is used to train these language models is the transformer machine learning architecture. You probably already heard of it. And this is based on deep learning. Yeah, and this is what is used nowadays to train these huge language models that are used in a natural language processing. Now, how can we learn these probabilities of the following next words? This is learned from the examples in the corpus. And by training the network, we try to adjust the weights of these connections between these artificial neurons. So for instance, if we have a sentence like, I was eating popcorns, and you want to predict a word like cinema, the model first predicts because this has the highest probability in the starting phase. This is wrong, of course, so you try to adjust the weights between the neurons to have a better prediction the next time. Next time I get bar, which is already better, but I want to have cinema, so I again will adjust the weights between the neurons in the network. And then finally, I get cinema, and I have improved my model until it has a good performance. So this is what it looks like. So you keep adjusting the weights until you have a reasonable performance, and you can predict the most probable next words for a given sentence. And then finally, when I have trained enough, I have done enough iterations to adjust the weights between the artificial neurons in my network. I have my final language model, which can be used to predict the probable most logical next word for a given sequence of words. Okay, so we know how to train our network, but how does it work in practice? So how can we build a language model starting from this huge text corpus? The intuition underlying the language model is the distributional hypothesis that you probably are all familiar with, or it already exists a very long time. So it states that you shall know a word by the company it keeps. So what does that mean? If you have a corpus, and you have words that occur in similar contexts, meaning they occur with the same kinds of words, they will probably also have related meanings. Yeah? Or otherwise put, we can deduce the meaning of a word by looking at the context of it in the corpus. So if you have, for instance, these 3 sentences containing the word bank, as a human, you know which meaning bank refers to by looking at the surrounding words in the sentence. Yeah? So for instance, in the first sentence, you know that it's the river bank because you see words like river or along. Even grammatical words can be very informative to know which meaning they refer to in this particular sentence. So we can know the meaning of a word by looking at the other words that surround this word in corpus. Now, how can we operationalize this distributional hypothesis? Because we know that computers, they cannot work with text, so they cannot look at words and sentences. So we will have to find a way to convert text into numeric vectors that computers can work with. And this is what we call word embeddings. You might have come across this term in the context of language models. So these word embeddings, they look a bit like our feature vectors that I talked about from more traditional approaches for machine learning. So we will try to convert our text into numeric vectors. And the numbers that are contained in these vectors, they contain information about the meaning of words, being the contexts in which the words occur in our corpus. Yeah? So this will allow us to represent words in a dimensional space. And you will see in the example I will show in a minute, that words that are semantically related, so that share semantic relationships, they will have similar vectors and it will be close in the vector space. So when you have a look at this example, I have simplified it because usually in the feature vectors, we have hundreds or thousands of dimensions. And one dimension gives you information about a given context, a word occurs in a corpus. So I have only kept 2 dimensions here. So I have, if you remember from your math courses, so you have a vector, it has coordinates. So we have on the x-axis, for instance, for the cherry example, we have 0.35, we do somewhere here. And then on the y-axis, we have 0.15. So this way, we can locate all the words in this geometrical vector space. So if you do this for all 4 examples, you see that indeed, because of the information that is contained in the vectors, that gives you information about the context of the words and the corpus, you see that cherry and strawberry are closer together in this vector space than, for instance, car and train. So this is how this works in a language model. So you look at the context and the corpus, you turn this into numerical information, and you store all this information into vector space. And then finally, we have our final language model, which looks like this. So you have words that are a bit clustered together in this geometrical space, but as all information is contained in numeric format, computers can work with this. So when you work with ChatGPT, the model does not understand what you ask, but it knows semantic and syntactic relations between words, and it can predict the next probable word. Okay, so we have built our big, large language model that can model a given language, but this model can only predict the next probable word. It cannot, for instance, give you a part of speech tag. So that's why we need a second phase. So this is the second step of fine-tuning. And fine-tuning means that, again, you will use your data set with manually labeled examples in order to further train the language model for a specific task. So for instance, if you want to build a neural model for part of speech tagging, you use your huge language model, but you adapt it specifically for the task of part of speech tagging by using manually labeled examples. So that's a bit in a nutshell. I hope it's a little bit clear. It was a bit fast, but I think it will allow to understand better what Gustav had explained.
Thank you, Els. Good. The OCR part. So I'll go now over the OCR and the NLP, and I'll assume that some of the terms that Els has just been presenting is more or less in your heads now. Otherwise, ask afterwards. So the OCR, our objectives are first to gather data, consistent data, and efficient annotation processes are essential for this part. The efficiency, I'll come back to a bit more, but efficiency plays a big role when you want to annotate individual signs on tablets, and you need a lot of data. Then there's the high quality data, which is essential, which we need, of course, for the analysis result, as Elvis just explained. But we also want to use it for sign list and paleography, so it can be used for astrological purposes or cuneiform purposes, cuneiform studies purposes outside of that. Then we have the computational analysis. In simple terms, we want to detect where objects are in image. We want to segment one sign from the other, so we know exactly where one begins and one ends. And then we want to identify the signs that they represent. And then lastly, after that, once we have a language model that can supplement here, we want to transliterate the signs. But that's a slightly different task because it requires something extra, so to speak. It requires to understand not only graphically what is the sign, but also need to understand in which context is it. We have around 200 texts, as I've mentioned, from Nippur and Boavieshu. These are, especially the Nippur texts, are very well known for our specialists, so that helps. They have been 2D plus imaged, and this basically means that they've been put in this big black dome where there's tons of different light from all over. And then you take a picture, and then you get a lot of different lighting angles you can manipulate digitally. So you can manipulate the lighting angles, but you can also generate computer versions which help you read as well. And I'll just start this little video on loop, which will show you the different lighting angles we use. So we kind of set some specific lighting angles because you can take a ton of different lighting angles, but we kind of set on 9 different ones. And then we have 3 different computer-generated versions. So I'll just start this one, and then you can see the different angles. Then we have the sign annotations themselves. They are polygonal boundaries. That means we have multiple nodes. So it's not just a square. We found that doing a square, you often sit and then try to reduce the noise by trying to fit it perfectly inside the box without taking too much of other signs. But it was just for us, and this is where the efficiency part comes in. It was easier to sit and then just surround the signs with a lot more nodes. Then you get less noise, and hopefully that will also improve our model. The training data we end up with 12 different images per sign. So the 9 different angles and 3 computer-generated images. You can see here 2 examples. So this is when light is from the top straight down, as far as I remember, on the left, and then it's sketch A, we call it. So one of the computer-generated versions. We also get the reading of the signs, and we get the ID of the sign, and then we get the index, where is it on the tablet. We get the coordinates of the polygonal boundaries, so we can extract that and nothing else afterwards. And then computer looks into the features, so that's basically what the computer sees, right? So you have on the left, you have sort of what the computer sees in black and white. It sees lines and where lines end and where lines go around. That's what it uses to understand what's happening. Whereas, as you can see on the right, that's how we understand what this example of a leaf is. We understand how long is the stem, or now I'm not taxonomist, so I don't know exactly, but you can see some of the words that they put in there to define the different leaves. What we then did was we tested a model called YOLO. You only look once. So the idea is that you only look once instead of having like a recurrent look at the model or the image, sorry. And here we try to detect and locate signs in square boxes, so not the polygonals, that's going to be for later. And then we try to identify the classes. So these are the small numbers you might see, and the color variation, that's the classes of the boxes. The results were decent, not fabulous, they were decent. I'm not going to show you the numbers now, because that's going to be part of a publication later, hopefully. But I'll just show you a few images of how it looks like. So you can see on the left, the ground truth. So that's the thing we would ideally have. We have a bit of issues with the classes, so not all signs have been found here. So you can see there are a few things missing, but that's so far the ideal. And then on the right, you can see there's a lot of boxes missing, and not all signs have been found. And here you can see the difference. So on the left, you have the ground truth on the far left, and then you have 3 different image versions of the same tablet. So the first one is the front, color 00, so that means light from straight above. You can see you have 31 predictions on this. So 31 places a computer assumed that it can see a sign and give us a class. And then you have the color B, which as far as I remember is from straight up on top of the tablet, so to speak. So not straight over, but if you take the light in front of you. And here you have 37 predictions. This is where, if you remember earlier, is where you can see the heads of the signs a bit more clear. So you can see already there's a big difference. And then the sketch A has 35 predictions. That's one of the computer-generated versions. So you can see that not only which kind of image you have, but also just way you manipulate the image you have can actually make quite a big difference. So what's next? We want to test more complex models. We want to test with polygonal boundaries rather than bounding boxes. And then we need to go in and redefine our classes. So we need to go in and clean out a bit, do a bit of housekeeping with that. We need to gather more data. So that means annotation. We need to see if we can combine data that's already there with the data we have. That can be a bit difficult depending on standards and image types and all that kind of stuff. And then we need to go out and see if we can collect data that's sort of in an intermediate space. So that can be hand copies. So when you try to make a copy by hand of how you think the sign should look like, you can do OCR of that if there's standardized in a certain way. And we might be able to take that and use that as data. Good. The NLP. This is where we've done most so far. And what we've focused on currently is the semi-automatic annotation part. So what we want to do is we want the computer to predict morphemes, lemma, and part of speech. We want to input transliterations. So that's, you can see in the red box, that's how the transliteration can look like. That's where you give the individual signs sort of space. So you indicate where they belong together with other signs, but you still have the individual signs visible. In this way, we maintain the spelling information. The output data we want is grammatical annotations. We do this instead of transcriptions, which is the standard way to do it. Transcription has below transliteration. That's where you interpret what you think the words should be. We do that to avoid identical forms such as the G perfect or the GT preterite. They are both similar. They look the same. So by using grammatical annotations, we can get rid of that issue. We use machine learning because the nice thing about that is it can possibly understand spelling variation and unattested forms. I have this example, which I really like. It's neither unattested or a spelling variation, or you can say it's a spelling variation. It's basically, we're missing half the signs. So it, ta, x, al. Most astrologists would assume that's a verb, but we chose not to tag it because it's quite broken. So we just left it untagged. But the computer actually found out, oh, this should actually be a verb. So I definitely agree with it. It should be a verb, but we just didn't tag it. Then we have the computational analysis. Here we want to try and quantify the words and the relations. That's the embeddings else we're talking about, sort of giving these vectors for where things are. And here we want to try to implement some methods that can help us based on those things to understand a bit deeper what's happening. We have a method called automatic term extraction, which is the computer trying to understand which terms are essential in the text and which terms mean something, and then extract those. We hope that can help us maybe identify subtopics of letters. So we know what's happening, maybe a part of the letter, what tend to be written together, those sort of questions, right? The answer. Then we have distributional semantic analysis, which is, I think, Alte's specialty even. So that's nice. Here we might be able to distinguish near synonyms. We hope to, for example, understand when do you use kapu versus sakaru, maybe especially in the imperative. So those kind of things can give us a sense of what is happening. And then we hope, big hope, but maybe to be able to identify social lets. So who and when do people use specific words in specific contexts? Because we have letters, so that means we know who it's to and we know who it's from. So we can maybe understand a bit more which words mean something in which social hierarchical context. Then we have the linguistic analysis, which we hope to, with these computational analysis, we hope to be able to get closer to the spoken language, because we have the assumption that the letters are the closest thing to spoken language, or at least a vernacular of some sort. That's of course a big statement, but of all the genres, we believe that one to be the best. We hope to be able to then understand a bit more of the everyday use language, and we hope maybe to be able to identify social language. We have so far 121 nice Ober-Babylonian Akkadian letters from SIPA. We've chosen SIPA so far because it's a relatively big corpus, only from SIPA. And by limiting the variation, we will also get fewer unique place names, for example. So we get fewer of the outliers and might be able to hopefully hone in on a good model for a lot of text quite quickly. And then we'll, of course, increase it after that. With a nice, I mean not very broken texts. So you can see here an example of a very rough surface text. This is relatively nice. It's not nice to read because it's very rough in the surface, but it's relatively well preserved. So it's not very broken, which of course means that we have as much content per text as possible. Currently, we have less than 10,000 words in our corpus. That means low resource. And they have been lemmatized in ORAC. We have just a very brief example of how it looks like in the bottom. And then we have added morphological annotation outside of that. And the goal, as I said before, is to get all Old Babylonian Akkadian letters into our system. So far, we have tested some model in the semi-automatic annotation. We have tested something called the Flare toolkit. I think it's even been actually developed, maybe not in this building, but at least in Humboldt, at Humboldt University. It's free to use and it's easy to use. It's a simple Python library. And also it has a pre-trained embeddings en masse, which is very nice. It has different languages, multi-language, that sort of stuff. So that also helps us a lot. And just on the right, you see just an example of how simple the training input and the testing output is. So this is, of course, a very simple label. It's just a part of speech tagging. It might be longer if you have other things. But here you have the transliteration, and then you have tab separated the part of speech tagging. And then below in the output, you just have what the ground truth, and then you have the computer prediction. So that's it. And you can see here that the computer guessed perfectly, predicted perfectly. We're trying to predict part of speech tagging and very simple morphological tagging. We are testing on 5 randomly divided folds. We test by 80% training and 20% testing. And what we want to test is first some different language embeddings. Then we want to test, is there a difference between Unicode, Cuneiform, and transliteration? And maybe I should go back and show you the Unicode Cuneiform there is above the transliteration. So it's basically the Cuneiform signs put into a Unicode manner so you can write them out on a computer. So we have seen a lot of, or some publication recently has tried to use Unicode Cuneiform with some positive results, and want to see if we experience the same and what we experienced when we were trying to do that. Because we had sort of the initial hypothesis that working with Unicode Cuneiform would get us closer to the original text, because after all, the Cuneiform signs and so are the ones on the tablet. Well, I'll get a bit back to what we think about that now. Then we tried text separation. So basically, when you put something into the model, you need to separate them into sentences. So if you give too much, too long sentences, more than what is an independent meaning of a sentence, you give too much of a context, you over-contextualize things, so to speak. And also, of course, increases the time it takes to get to things. But if you make them too small, things doesn't have enough context to hang on to. So that's the fine line we have to figure out which gives us the best results. The results I'm going to show you is going to be average accuracy. So over these 5 random divided folds, it's going to be the accuracy only. With the language embeddings, we try to predict part of speech tagging and some simple morphological tags. Our input was transliterated text, which was separated by verbs. And we tried the multilingual, Arabic, Spanish, and Japanese. Well, multilingual was kind of sort of the idea of, universal language model idea that, the more languages, the better it understands languages. Arabic was sort of the idea that it's a Semitic language, so it's Akkadian, should maybe try that one. Spanish was to have something else, so an Indo-European language that doesn't seem to have any relation to Akkadian. And then Japanese, I'll get back to why we also tested Japanese. And Arabic outperformed all of them, not gloriously, but quite decently. So we kind of concluded that Semitic languages are most likely the best way to build kind of the basis on first, and then we can fine tune later. So because then you have some Arabic, you have Hebrew, which are both 2 quite large resource languages, and then of course you have a bunch of other lower resource languages you can hopefully kind of join in the group later. Then we have the question of Unicode Cuneiform. So what we did, we tried to predict only POS tags here. Guess with Unicode Cuneiform, we would have 2 poor results if we had tried anything else than that. The input was text separated by verbs in either transliteration technique. We have the same pre-trained embeddings here. And as you can see with the transliteration, Arabic performed the best. And with the Unicode cuneiform, Japanese performed the best. And we tried Japanese because it is also it's also written with a local syllabic script. So Arabic is written with an abjad, so it has a different script system or uses different script compared to cuneiform. Whereas Japanese uses a system that has the same type as the cuneiform writing system. So that's why we tried that, and it was also proved useful. So that didn't show us much other than it's performing a lot worse, and that it might be worth including Japanese, maybe in a model that wants to look at Unicode cuneiform, maybe in the model that works with OCR, who knows. Then we tried to test the text separation. So as I said, the idea was how much text you include in each sentence you give the language model. Here we tried text separated. So every time you have a new text, we separate. We tried line separation. So on the tablet, you typically have actual lines written out with a ruler, but it almost we call the ruling. And we separated by verb. Because we have this information, we could separate by each verb. And each verb was the best performing model of the three. Again, not gloriously over lines, but that's because line separation is sort of close to the verb separation in length. We came across a bunch of problems, but I'll just go through a few of them here. First was the data format. There is a very inconsistent way of doing data formatting across digital assyriology. It's also a relatively new field, so not so surprising. And there's for our purpose at least, the data formats which dominates are insufficient. Might be very sufficient for other purposes, but for our purpose, it's sufficient. So there is the ASCII transliteration format, the ATF, which is the dominating one on ORAC, which for our purpose is just not useful. So we, with some other people, are switching over to something called Conlu, their standard, and trying to develop something that fits better our purpose there. Then there's a question of how do we even represent Semitic languages? So a lot of these definitions, the part of speech, for example, is based on Eurocentric research. Basically mean that the way Semitic languages build up words is not necessarily in the idea of here you have a verb, here you have a noun, here you have an adjective. Those kind of division doesn't exist in the same way as we see it in Indo-European languages. And that's, of course, can create problems when we're trying to make our data fit into these boxes of, are we looking at a verb or are we looking at an adjective or a noun? So these are things we have to discuss. And if you look at standards used by Arabic or Hebrew, for example, they also kind of disagree with how to go down. Do you have to do more of the way we look at the language as Eurocentric researchers? Or should you do more of an emic way of looking at it and saying, okay, this specific form does something like transitivity, for example, it's passive, whatever. Or should we do that instead and trying to do very down in the gritty grammatical part and try to explain the functionality rather than the groups we have defined? Then we question what is the value of Unicode cuneiform. We, after some deliberation, do not think we get closer to the at least I don't, to the language itself, because it's in this case where we have the language, the transliteration, and then go to Unicode cuneiform. It might look more like the tablets, but it's basically just an ambiguation of the transliteration. So that basically means when the transliteration is a specific reading of a sign, we say, okay, out of these 10 different readings of a sign, this one is the one we believe to be correct. We then just reverse it and say, okay, now we just tell you can be 10 different sign readings. And that makes it, of course, a lot more complicated for the computer. And we would like to test a bit more if with human experiments, sounds so horrible, but with experiments including humans, where we would like to try and see if that's true. Then we have the Ober-Babylonian Akkadian itself. We are questioning a bit about how do we work with the language in an NLP this way. So we took, for example, the subject-object word order as the basis for the verb separation, as I mentioned before. This is the most standard way they write their word order, but there are also nominal phrases, for example. So how do we consider a nominal phrase? Should we separate that? And how do we do that with the information we have? So what then happen is that in our system, the nominal phrase just becomes sort of a preamble to a following verb that comes afterwards. Then we have the idea of like, when does an independent clause, when is it independent enough to be a different meaning, completely independent? And should we always include subordinated clauses, stuff like that? That's the questions we're kind of battling and see if we, with the data we have so far, can come out with a system that gives us the best model. There are things that could help this along. There are something called tree banking, which could help this. Then we draw the relations between the different sentences. But the issue there is that it's very time consuming and it just doesn't fit into the project we're doing right now. But that might be a future thing to try out. Right now, what we're trying to do is then to improve our semi-automatic annotation. We want to enlarge our pipeline. So first we have to gather all machine-readable Old Babylonian Akkadian letters we can. Then we need to go into bigger language models, more efficient language models, and try to see what works best for us. This means, in this case, ditching a flare. And then try to see if we can figure out, when we then put something in there, what are the typical mistakes we get out the other end. Then we run chunks of these machine-readable Old Babylonian Akkadian letters in there. So I mean, maybe take 20 at a time, put that in, get it out the other end, and correct what we expect to be mistakes, and of course, see if we find out the mistakes along the way. And then we repeat that process, but finding out, okay, hopefully fewer and fewer mistakes at each iteration. And then at the end, we will have a fully annotated corpus. So after that, we want to, as mentioned, do the two different computation analysis, the automatic term extraction and the distributional semantic analysis. We hopefully will showcase the value for cuneiformists of using these methods. Then, of course, sharing the data is extremely important for us. We will do that in an ORAC project at some point. And then the rich annotations, which we cannot fit into ORAC in the way we see fit, we will, of course, share that on another platform, which is still unknown. And all of this will, of course, be open access. So just quickly summarize what I've been talking about and saying what's next for our project. Then I'll leave it. So we want to showcase the value of digital and computational humanities for cuneiform studies and in general, of course. We really want to help create a more open access cuneiform corpus. That's very important for us, that not only we can access more stuff out there, but also that people can access our stuff freely and just remember to refer stuff correctly, of course. And of course, we want to further cross-discipline collaborations, not only for getting more research funding, that's nice, but also because we believe that it gives you the best results to do so. The more tangible result is that we want to provide valuable digital publications for researchers in a broad sense. I've experienced economic scholars from random UK universities saying, oh, we have data, can I have it? And the issue is that, yeah, I have data, but I don't have it in a format that you can use. And that's extremely important that we, as a relatively small field with a very niche text corpus that is huge, but still very niche in many people's eyes, that we deliver things that other people can also use in their research. We want to create an automatic cuneiform sign recognizer for Babylonian Akkadian, which of course very difficult to do, but that's our goal. And then we'll conclude on some computational linguistic analysis of Old Babylonian Akkadian letters and see how it works. The next thing concretely is we're gonna test some of the criteria we have for our IIIF viewer and see if it's feasible, can be done in the time we have, and is it what we actually need when we're sitting with it in front of us on the computer. Then we want to increase the data, for the OCR and for the NLP. And then we want to map out the computational pipelines for these two projects as well. That's it. Thank you. Maybe I'll just quickly add that we're funded by Bellspoke, and you can scan the QR code with some of the literature and some information on the pictures and stuff like that. Yeah, thank you.
Thank you very much for this comprehensive overview. I now see that when we were talking before, and I said whenever I try to tackle a research question, I have 3 more projects because I have to do the digitization first and then the NLP first. Now I see it's the same for you. So I feel quite understood. Thank you. Gustav, can you please stop sharing so that we can see the other participants online better?
Yes,